Hi, I'm Sam. Group members are on the screen. We're going to be discussing extended Newton's method today. So, if you may or may not have done linear dynamical systems as a subject last term, it was covered in that. But in case you don't know, Newton's method is basically a iterative equation that we can use to approximate the zeros of a function. In the case of a single variable function, such as f of x equals x squared minus 2, we're finding when f of x is equal to 0, which is the red dot on the screen. This is the method you see in the slide. You have a breakdown of your different values. X of n is either the output value of the previous iteration of the method, because it's iterative, you constantly do it. You constantly get x of 0, x of 1, x of 2, x of 3. If you're just starting off with the method, x of n can be an initial input value, which is relatively close to the true value, i.e. the red dot, but we want to somewhat get a generalized trend towards the value. So imagine you don't know the true red value. Um, Then for the second part, we have the output values of the function at x of n over, and then the denominator, sorry, is the value of the derivative at x of n. So as you continue doing the iterations over and over again, you get closer and closer to the true value of the root. Now, here is extended Newton's method, which we use for multivariable functions. Um, this is somewhat of a similar method to the single variable one. However, in this case, we use something called the Jacobian matrix. If you don't remember the Jacobian matrix, we covered it in lecture 16, where it is essentially a matrix containing the partial derivatives of a set of equations with regards to their different unknown variables. So in the multivariable method, what we do is, instead of finding the roots of the function, we find where the functions intersect with each other. So we're mainly focusing on two variable functions. Another thing with this method is that in order for it to work appropriately, we need to make sure that the Jacobian is a square matrix in order for it to be invertible, as shown on the screen, due to the -1 index. So you need to have n number of equations with n number of unknown variables in them in order to make sure that you can invert it. I will now pass over to Nicola.
Hi, I'm Nicola. So, although the Newton's method is really useful, there are some pitfalls to both the single variable and the two variable method. So, for single variables, Newton's method will fail in the case where there is a derivative equal to 0. This is because the fraction of the f of x of n over the derivative will be undefined because you can't divide by 0. Additionally, if the function is not continuous at a given point, or like not differentiable, the method will also fail because you can't actually complete the formula. Also, if a function has a vertical tangent at any point, such as x equals a, then Newton's method wouldn't work. An example of this is y equals x to the power of a third. This is because by using this method on a guess, let's say x equals to 1, your value is going to, for like each of your guesses, so x equals x for 2, x3, x4, they're actually going to increase in value rather than converging to a given point. And then Newton's method is dependent on a good initial value choice. So if you don't choose a value close enough to your desired root, then you're actually, you could end up at the wrong root, or you could just continue going away from the route that you actually wanted to. And this is evident in the graph to the right. Yeah. And then for two variable, you also have most of the pitfalls from single variables. So if the derivative is being equal to 0 or the function is not differentiable, you actually won't be able to complete Newton's method. And at if any stage of the iteration with the multivariate method, the Jacobian matrix isn't invertible, the formula cannot be used. This can actually be solved by changing the initial input values, but it depends on your initial input values as well. So you also need to have good values to choose from. So yeah.
Hi, I'm Charlotte. I will give an example of the extended Newton's method. So to begin, we need to guess an initial vector. So I just guessed x is 1 for both x is 0 and y is 0. Then we must calculate the partial derivatives of both equations. And then using this, we need to find the Jacobian matrix that Sam mentioned earlier, which will then let us find the determinant that we can use to calculate the inverse. Once we find the inverse, we can use the formula from slide 3, and we can substitute our values in. This will let us simplify it, and we find like a final equation for the method. And then we can substitute our initial values that we guessed earlier, and this will create like x of 1 and y of 1. And then using the answers that are resultant from that, we can find x of 2 and y of 2, and then you just keep going until the value, converges to one number, as shown in the table. So then we can prove that these are accurate through simultaneous equations and substituting the values we find for x and then using that to find y. So then it will provide the values that should directly match to the extended Newton's method. And yeah, therefore Newton's method can provide accurate values for the intersections of two equations, as shown in this example. So we'll move on to Ellen.
Hi, so this is another example with different equations. So you're finding the intersection of the 2 points through extended Newton's method. So the first step would be to define the function. And then we have to make an initial guess, which would be, we have guessed x0 equals a half and y0 equals a half. And so we then use the formula of x to the k to work out Newton's method. So we can find the Jacobian matrix here, and then we have to find the inverse matrix as in the formula. So use the formula for the inverse of the matrix of a Jacobian matrix. We then simplify it to get the value here. We then sub it back into the original formula. We can also consider the example without the x minus k to make it more more simple to multiply the two matrices together, taking out 1/6 as a factor on both of the matrices and then simplifying it. We then again sub it back into the original formula we were using to get this value. And then we are subbing back our initial guess from the beginning to get x1 as 11/12, and y1 7/12. We then repeat this as many times as you want. In this example, I've done to 3, and the more you do, the more accurate your results are. And that's the end of our presentation. Thank you for listening.
Thank you.
Awesome, guys. Thank you so much for the work that you've put in. I do appreciate how confronting such a thing can be, to go away yourselves and address some thing that you've not been overly prescriptive about, but in the vein of what's been going on today. Thank you. It's wonderful. Has anybody got any other comments or questions? Okay, so let's move forward. Thank you. Thank you.
Do you want us to go next, sir?
Yeah, absolutely. If you're ready to go, I'm happy for you to go.
All right, cool.
Take it away.
All right.
Hello, I'm Achinta, and I'll be starting off with the introduction. The Monte Carlo method of integration is a method of integration which provides an approximation to a definite integral through the use of random sampling. The creation of its modern version can be attributed to the late 1940s, where Stanislav Ulam invented the method while working on nuclear weaponry. The name Monte Carlo was actually a code name to mask its involvement in the Manhattan Project and is a reference to the Monte Carlo casino located in Monaco, which in itself is a direct reference to the random nature of the method as can be attributed with gambling. Due to the random inputs, Monte Carlo integration is considered a non-deterministic method. That is, the answer won't necessarily be the same every time the integration is done. And as a result, it only gives an approximation of the answer. However, this approximation can be very, very accurate as the number of the sample points increases. So does accuracy, all while being less computation intensive when compared to other conventional deterministic methods. Uses. The Monte Carlo method of integration is widely taken advantage of through the multiple industries, with the most common being physics and mathematics. It is often used as an alternative approach for situations where conventional deterministic methods are impossible or infeasible due to large computational requirements involved. In the field of physics, the method is heavily utilized for simulating systems with large degrees of freedom, such as fluids, particles, and coupled systems. It can be dated as far back as the 1930s, where it was first used in the study of neutron diffusion. However, its most interesting use cases is its role in the design and development of nuclear weapons. The method played a central role in the Manhattan Project in the 1940s, as well as the Los Alamos in 1950s during the development of the nuclear bomb and the hydrogen bomb, respectively. The Monte Carlo method of integration is also heavily utilized in the field of mathematics, specifically for integration with high dimensional calculations. This method serves as a powerful alternative to conventional deterministic methods of integration, such as the trapezoidal rule, solving indefinite integrals of higher dimensions with greatly reduced computational cost and time. However, as it is based on random sampling, as the amount of samples increases, so does the accuracy and computational cost as well, and vice versa, allowing mathematicians to easily prioritize either accuracy or computational cost when doing their calculations. Furthermore, the Monte Carlo method of integration is also taken advantage of in a plethora of other fields, such as engineering, computer science, chemistry, and even in the business and finance sector. For example, in engineering, the Monte Carlo method is, for example, in engineering, the Monte Carlo method is used to make predictions of failure and cost overruns in relatively high accuracy. In computer science, it is utilized in the calculation of signal processing and Bayesian inference. In chemistry, it is commonly used for genetic calculations, while in the business and finance sector, it is primarily involved in risk calculation.
Hi, my name is Jose, and I'll be talking about the process of the Monte Carlo integration. The process of the Monte Carlo integration usually follows 3 key steps. First, you need to calculate the size of the target area and then randomly plot your points. In the image on the left, the line y is equal to 2 to the power of x is plotted in red. The green line shows the target area, which goes from x is equal to 0 to 2 and y is equal to 0 to 4. The size of the target area is 8 units squared. 10 blue points have also been put in the target area. The second step is to compute the number of points in the area you want to find the size of. In our example, there are 4 points that lie under the curve, now shown in orange. The third step is to divide the points under the curve by the total number of points and then multiply by the total area. We have 10 points in total, so we divide 4 by 10 and then multiply 8 to get 3.2. The answer 3.2 is a fair bit off the actual answer of 4.33. This is primarily due to the low sample size of 10, but is also partially due to the randomness of the points being assigned. As in our example, only 4 points were below in the curve. If 5 points were below the curve, the answer would have been 4 units, which is much closer to 4.33.
My name's Samuel. Before we talk about increasing the accuracy of our answer, there are a few things to consider regarding the random placing of points. It is technically considered to be impossible to generate truly random numbers, as an event always has an event occur before it. This means that the former event is influenced by the latter event, and if the former event was known, then the outcome of the latter event could be predicted. For example, imagine you were flipping a coin. If you knew everything that would influence the flip, such as the speed and direction of the wind, the strength you put into the flip, and any damage to the coin that would influence its rotation, then you could predict what side would land face up with complete accuracy 100% of the time. Random number generators usually use pseudo-randomness, which is generally considered to be sufficient. However, many large-scale random number generators use external events such as weather patterns, atmospheric noise, or the radioactive decay of an atom. Some random number generators even use data from the cosmic microwave background, which is radiation speculated to be left over from the Big Bang, and is considered one of the most random things in existence. In order to get a more accurate answer, more points can be plotted randomly. It reduces the effect of outlier points and generally gives a more precise answer. Doing this by hand can quickly become tedious, so computers are used for these calculations instead. In the code on the left, we can find the area of a circle with radius of 1 by plotting 1,000,000 points. Running the code gives us a very close approximation of the area of the circle at 3.141312. The actual value is 3.14159, or pi to 5 decimal places. If we ran the code for a much smaller sample size, like plotting 100 points, we get 3.28 as our answer. Plotting just 4 points gives us 2, a result which is quite far off.
Now we can try some more examples. Let's say we want to find the integral of the natural log of x over x between the bounds of 1 and 10, shown on the graph on the right. In this example, we are using our 100,000 randomly plotted points. If we run the code, we get 2.6504, which is very close to the actual answer of 2.6509.
Here we have a more complex example, finding the integral of 3 times x to the power of 4 plus half y squared, where both x and y are between -3 and 3. This example also uses 100,000 randomly plotted points. We plot all these points and put them into our function called g. Then we find the mean of all these points and multiply by 36, which is the total area. This gives us 1,806.7894, which is very close to the actual answer of 1,803.6. And that's it.